Practice exam number 2. So the problems on this practice exam are nearly identical to those problems that you have on your actual exam. The majority of problems will look identical, but maybe the only difference is the numbers may be different. So let me do problem number 1. Oh, and I guess when I go over this exam, I will give you several different techniques to be able to solve a problem. When you solve a problem, you'll only be using one of the techniques. Maybe you will decide that you want to use the TI-84, and you'll follow those steps that I give you for the TI-84, or maybe you want to do everything by hand, and you'll follow those steps when you do everything by hand. So I may give several differing solutions to one particular problem, but in your particular case, you'll only be doing one of those. When I do a problem, the amount of work that I show is the amount of work that I would expect that you would show on your PDF. And if you did not show the same amount of work on your PDF, you may not get full credit. You may get little, if any, credit if you do not show any work on a particular problem. So let me do problem number 1. 26 of 110 digital video recorders, DVRs, in the inventory are known to be defective. What is the probability that a randomly selected item is defective? Express your answer as a percentage rounded to the nearest hundredth without the percent sign. Let D be the event that the DVR is defective. I want to find the probability that, well, the randomly selected DVR is defective. Well, 26 of the 110 are defective. And so I get 0.23636363636. Rounding, moving my decimal place 2 places to the right, I have 23.6363636%. Rounding to the nearest hundredth of a percent, well, I have the digit 3 here. The digit immediately to its right is a 6. Since 6 is greater than or equal to 5, then I'll round the 3 up to a 4. So 23.64%. Problem 2. Use the data in the following table, which lists drive-through order accuracy at popular fast food chains. Assume that the orders are randomly selected from those included in the table. And so here's my table. If one order is selected, find the probability of getting an order that is from restaurant A or an order that is not accurate. Express your answer as a percentage rounded to the nearest hundredth without the percent sign. So let A be the event that the order is from restaurant A. Let N be the event that the order is not accurate. So I want to find the probability that of A or N, the probability that my order is from restaurant A or that is not accurate. And so let's add these all up. So 17 plus 10 plus 19 plus 20 plus 22, 88 over, well, let's find the grand total. So first, let's add up each column. So 39, 15, 22, 41. And then let's add all these up. So 39 plus 41, 80, plus 15, 95, plus 22, 117. And so we have 88 over 117, 0.7521367521. Move my decimal place 2 places to the right. So 75.21367521%, round to the nearest hundredth of a percent. And so 75.21%. Problem 3. Use the data in the following table, which lists drive-through order accuracy at popular fast food chains. Assume that the orders are randomly selected from those included in the table. And so here's the table. If 3 different orders are selected, find the probability that they are all from restaurant B. Assume that the orders are selected with replacement. Express your answer as a percentage rounded to the nearest hundredth without the percent sign. So let B be the event that the order is from a restaurant B. And so let's add up each of these. So I have 43, 95, 50, 35. Let's add up these. We get 103, 120. Let's add up these. So we get 223. So let's find the prob. So I want to find the probability that, well, the first one that I pick is from restaurant B. Well, let's see. 95 of the orders are from restaurant B out of a total of 223 orders. So it's 95 out of 223. Now, since we assume that these are selected with replacement, then each of the events are independent. So selected that was from, restaurant B or whatever, well, or any of the other restaurants, then you put it back into the pile again. And so there will still be, for the probability that the second one that you choose is from restaurant B, it will still be 95 or the 223. The probability of the third one that you choose is from restaurant B will still again be 95 out of 223. And so it's 95 out of 223 quantity cubed, 0.077313658 Move my decimal place 2 places to the right, 7.73136589%, round to the nearest hundredth of a percent, 7.73%. Problem number 4. Use the data in the following table, which lists drive-through order accuracy at popular fast food chains. Assume that the orders are randomly selected from those included in the table. If one order is selected, find the probability of getting an order from restaurant C given that the order is accurate. Express your answer as a percentage rounded to the nearest hundredth without the percent sign. Okay, so we want to determine the conditional probability. We are given that the order is accurate. So I'm going to restrict my sample space to only those where their order is accurate. There's a total of 87 of those. And so we have a total of 87 orders that are accurate. Of those, let C be the event that the order is from restaurant C, and let A be the event that their order is accurate. So I want to find the probability of C given A. And so I restrict my sample space to only those from restaurant C. And so there'll be 20 out of 87 because I've restricted my sample space to only those where the order is accurate. And so 20 out of 87, 0.2298850,575. Let me move my decimal place 2 places to the right. So 22.98850,575%, round to the nearest hundredth of a percent, 22.99%. Problem number 5. A study conducted at a certain college shows that 38% of school's graduates find a job in their chosen field within a year after graduation. Find the probability that among 8 randomly selected graduates, at least one finds a job in his or her chosen field within a year of graduating. Assume that the sample is taken with replacement. Express your answer as a percentage rounded to the nearest hundredth without the percent sign. So I'm going to look at the complementary event. It's easier to, we're trying to find at least one. And so it's easier to find, rather than at least one, to find the complementary event of at least one. I have here that this is a binomial distribution, a binomial random variable. I have a fixed finite number of independent trials, 8. I have a success for each trial, which is that the college graduate from this school finds a job in his field within 1 year of graduating. And we have a fixed probability of success for each trial, 0.38. So I want to find the probability of at least one. And so I want to find the probability that X is greater than or equal to 1. And so let's look at the complementary event. Find the probability X is less than 1. Well, there's only one number less than 1, 0. So we want to find 1 minus the probability X is 0. So 1 minus, in this case, I'll use the binomial probability formula. So 8C0, 0.38 to the 0. If I have a 38% probability of success, I have a 62% chance of failure. So 0.62 to the power 8 minus 0, 8. And so 1 minus 0.62 to the 8th, 0.9781659894. Let's move my decimal 2 places to the right. So 97.81659894%. Let's round this to the nearest hundredth of a percent. So 97.82%. I can also use my TI-83, TI-84 to find this. So again, we'll be using the complementary event. This is a binomial distribution with n equals 8, p equals 0.8. So to find the probability X is greater than or equal to 1, I'll just do 1 minus the probability X is 0. So I'll use the binom PDF command. So 1 minus binom PDF 8, 0.38, 0. And so let me use technology to compute this. And so let me input 1 minus binom PDF. There are 8 trials, 0.38 probability of success for each trial, and I want to get rid of the 0. And so I get 0.9781659894. And so let me put that, let me write that number down. And so we have here 0.97, oops, 0.978165989894. And so moving my decimal place 2 places to the right, I have 97.81659894%. Rounding to the nearest hundredth of a percent, I have 97.82%. Well, we can also use Excel. So let's use Excel. So again, we'll be doing the complementary event. We have a binomial distribution with n equal 8, p equal 0.38. I want to find the probability x is greater than or equal to 1. So let's find 1 minus the probability x is 0. So 1 minus binom dist 0, comma 8, comma 0.38, comma false. And so let me use my Excel to calculate this. And so I'll do 1 minus binomial distribution, where I'll get rid of everything less than 1. So get rid of 0. I have 8 trials and a probability of success of 0.38. And I'll use the PDF. And so I have here 0.97816599. And so let me write that on my iPad. And so we have here 0.97816599. Let me move my decimal place 2 places to the right. And so I have here 97.816599%. Rounding to the nearest hundredth of a percent, I have here 97.82%. So I can use Mathematica to do this. So again, I will be using the complementary event. We have a binomial distribution. N is 8, P is 0.38. I want to find the probability that X is greater than or equal to 1. That's 1 minus the probability that X is 0. And so I'm going to do 1 minus PDF, binomial distribution, 8, comma 0.38, comma 0. And I'll evaluate that. So let's use Mathematica. And so let me type in the following command. And so 1 minus by the PDF for the binomial distribution with parameters 8.38. And I want to get rid of everything less than or equal to 0. And so I get here 0.978166. And so let me type that into my computer. And so I have here 0.978166. Move my decimal place 2 places to the right. So I have 97.8166%. Rounding to the nearest hundredth of a percent, I have here 97.82%. And so let me use R. And so we have a binomial distribution. N is 8, P is 0.38. I want to find the probability X is greater than 1. So the same as finding 1 minus the probability X is 0. So I'm going to type in 1 minus D binom 0, comma 8, comma 0.38. And so let me do that. And so let me type in 1 minus D binom. I want to get rid of everything less than or equal to 0. 8 and 0.38. Well, I guess I'm just getting rid of 0. And so I have 0.978166. So let me type that onto my computer. And so we have 0.78166. Let me move my decimal place 2 places to the right. So 97.8166%. Let me round to the nearest hundredth of a percent. So 97.82%. Okay, we can also use StatDisk. So let's use StatDisk. And so we have a binomial distribution. N equals 8, P is equal to 0.38. I want to find the probability that X is greater than or equal to 1. And so let me use StatDisk to do this. And so I have here, first, go to StatDisk, click on Analysis menu, and then from the probability distributions, click on Binomial Distribution. And so now, let's put in the number of trials, 8. The probability of success, 0.38. And I want to do everything from X greater than or equal to 1. So let's plug in 1. So if you do that, you look over here, and you see that you get the probability X is greater than or equal to 1 is 0.978181. 660. Okay, so let me type that into my computer. And so we have there. And so I have 0.978166. Move my decimal place 2 places to the right, 97.81660%, round to the nearest hundredth of a percent. And so I have 97.82%. Let me do problem number 6. In the town of Maplewood, a certain type of DVD player is sold at just 2 stores. 58% of the sales are from store A, and the rest of the sales are from store B. 7% of the DVD players sold at store A are defective, while 8% of the DVD players sold at store B are defective. If Kate receives one of these DVD players as a gift and finds that it is defective, what is the probability that it came from store A? Express your answer as a percentage rounded to the nearest hundredth without the percent sign. And so I have here that, well, we have 2 stores, store A and store B. We have that 58% of the sales are from store A, and the rest are from store B. So 58% are from store A, and the rest are from store B. And so, well, if I have a 58% probability of success, I have a 42% chance of failure. And so there's a 42% of the sales are from store B. Let D denote the fact that the DVR is defective, and N, the fact that the DVR is not defective. So we have that 7% of the DVDs from store A are defective, whereas 8% of the DVD players from store B are defective. So 7% from store A are defective, whereas 8% are defective from store B. Well, if I have a 7% chance of success, I have a 93% chance of failure. For an 8% chance of success, I have a 92% chance of failure. And so 93% of those DVD players from store A are non-defective, whereas 92% of those DVD players sold from store B is non-defective. I want to find the probability that of A, that the DVD player is from store A, given that the DVD player is defective. And so I want to find the probability of A given D. Well, I can find the probability that is defective, given that it's from store A. But if I know that it's defective, well, I don't know if it's from store A or store B. Therefore, I have to use Bayes' theorem. And so I want to look at all those that are defective. So let me multiply 0.58 times 0.07, 0.0406. That's 5.42 times 0.08, 0.0336. Those are the only ones that are defective. So let's add these up. So I get 0.0742. That will be my denominator. I want that it's from store A. And so my numerator is 0.0406. And so I get 29 over 53, 0.54716981113. Let's move my decimal place 2 places to the right. And so 54.716981113%. Let's round to the nearest hundredth of a percent. So 54.72%. Problem number 7. How many ways can 3 people be chosen and arranged in a straight line if there are 11 people to choose from? And so this is going to be an ordered arrangement. And so we're going to be using a permutation. So I'm going to look at NPR. And so I have 11 and I'm choosing 3 of them. So for the first one, there are 11 people I can first choose to be the first person in line. After I've chosen that first person, then there are only 10 people remaining that I can choose from to be in line. After I've chosen the second person, there's only 9 remaining. I can also use permutation, NPR. And so let's click on Math. Let's go to the PRB menu and let's select NPR. Oops, sorry. Let's input 11. Let's click on Math. Let's go to the PRB menu and select NPR. And I want 3 of them. And so I get 990. Okay, so let's put that number into my laptop. And so I have here that inputting 11 in PR, 3, I get 990. I could also use Excel to do this. And so let me use Excel. And so with Excel, I'll be using the command permute 11, 3. So let me do that. And so I have here permute 11, comma 3. And so I get 990. And so let me input that into my laptop. So let's write that down. And so we get that 11p3 using the permute 11, comma 3 command is 990. Let me do problem number 8. Library is to be given 5 books as a gift. The books will be selected from a list of 18 titles. If each book selected must have a different title, how many possible selections are there? Okay, so in this case, it doesn't matter the order at which you're selecting these. And so because of that, we'll be using a combination. And so we'll be looking at the NCR. And so in this case, well, there are 18 books, and we're going to be selecting 5 of them. And so 18, choose 5. And so I have 18 times 17 times 16 times 15 times 14. I start with 18 and I write down 1, 2, 3, 4, 5 numbers. Divided by factorial, 5 times 2. Well, 15 divided by 5 is 3. 16 divided by 4 is 4. 18 divided by 6 is 3. Times 17 is 51. Times 12 times 14 is 85, 63. And so I could also do this using technology. So let me do this on the TI-83 / TI-84. And so I'm going to do 18C5. And so let's input 18, click on Math, go to the PRB menu. It's the third one down. And let's select 5, hit enter. And so you get 85, 68. Let me type that into my laptop, into my iPad. And I have here CR5, and I get 60. Let me use Excel using the combine formula. And so I'll do 18C5 will just be combine 18, comma 5. So let me do that on my computer. And so I have here combine 18C5. And I get 8568. Okay. Let me write that on my iPad. And so I have here that if I were using Excel, then I would get 8565. I could also use Mathematica to do this. And so let me do 18C5. In this case, I'm going to be using the binomial coefficient in Mathematica. So I'm going to be doing binom 18, comma 5. Okay, so let me do that. Type in that command. And so I have here the binomial 18, comma 5. And so I get 8568. let me write that on my iPad. And so we have, 8568. I could also use R to do this. So let me show you how to do this in R. And so I'll just use the choose command in R. And so let me type in choose 18, 5. And so again, I get 8568. Let me type that into my iPad. Okay. So using the R, I get 8568. Problem number 9. Find the missing value required to create a probability distribution, then find the standard deviation for the given probability distribution. Round to the nearest hundredth. So in this case, well, we have here a distribution that is missing one number. Note that in order for us to have a discrete probability distribution, that all the probabilities here must be greater than or equal to 0, and they must add up to 1. So I have to have that all the probabilities are greater than 0, and they must all add up to 1. So therefore, whatever is missing must be the difference between the sum of these values and 1. And so let's do 1 minus 0.02 plus 0.18 plus 0.11 plus 0.06, 0.63. We also want to find standard deviation for this distribution. So I must attach 2 additional columns to my distribution, the x p of x column and the x squared p of x column. So to get the third column, the x p of x column, I multiply first and second column. 0 times 0.02, 0. 1 times 0.63, 0.63. 2 times 0.18, 0.36. 3 times 0.11, 0.33. 4 times 0.06, 0.24. To find the fourth column, I'll multiply the first and third column to get the fourth column, the x squared p of x column. 0 times 0, 0. 1 times 0.63, 0.63. 2 times 0.36, 0.72. 3 times 0.33, 0.99. 4 times 0.24, 0.96. Let's add up each of the columns. So this adds up to 1. Good. That means that this is a discrete probability distribution. Let's add up this column. I get 1.56. Let's add up this column here. So I get 3.3. So my variance is the sum of the last column, the x squared p of x column, 3.3, minus the square of the sum of the previous column, the x p of x column, 1.56 quantity squared. And so I get 0.8664. To find the standard deviation, I'll take the square root of the variance. And so the square root of 0.8644. Therefore, the standard deviation is 0.9308061023. I want to round to the nearest hundredth, and so 0.93. Let me do problem number 10. A 28-year-old man pays $228 for a 1-year life insurance policy with coverage of $13,671 if the probability that he will live through the year is 0.995, what is the expected value for the insurance policy? Round to the nearest cent. Okay, so I want to find the expected value. So let us set up a table here, a probability table to determine. And so we have that there is a 99%, 90.995 probability that he will live throughout the year. And so there's a 0.995 probability that he lives throughout the year. Therefore, there is a 0.005 probability that he does not live throughout the year, a year longer. He must pay $228 for his life insurance policy. If he lives, well, he's paid $228 and that just goes down the drain. And so he loses the $228. However, if he does not live, he dies within 1 year, then the insurance policy pays him $13,671. He had to, however, pay $228 for that. And so he will have made $13,448 if he dies within 1 year. Let's find the expected value. And so the expected value is just the sum of x plus. We'll attach this additional the xp of x column. Let's multiply the first and second column to get the third column. Oops. The first and second column here to get the third column. And so negative 228 times 0.995 is negative 226.86. Let's multiply 13,448 times 0.005 to get 67.215. Let's add these up. So I get a negative 159.645. Therefore, the expected value of the insurance policy is a negative $159.64. So you expect that you will lose some money because you don't, it's very unlikely that you're going to die within the first year. Problem number 11. According to a college survey, 84% of all students work full-time. Find the standard deviation for the number of students who work full-time in the sample of size 219, rounded to the nearest 100. So this is a binomial distribution. We have a fixed finite number of independent trials, 219. Success is that they work full-time. The probability of success is 0.84. I want to find the standard deviation. And so let's find the variance for the binomial distribution. So the variance is given by NPQ. So N is 219, P is 0.84. If I have an 84% chance of success, I have a 16% chance of failure. So Q is 0.16. Let's multiply these together. So I get 29.4336. And so to find the standard deviation, I'll be taking the square root of the variance. Well, the square root of 29.4436 is 5.425274187. Let me round that to the nearest hundredth. And so 5.43. Problem number 12. An archer is able to hit the bullseye 42% of the time. If she shoots 12 arrows, what is the probability that she does not get exactly 4 bullseye? Assume that each shot is independent of the others. Express your answer as a percentage rounded to the nearest hundredth. So in this case, we have that this is a binomial distribution. We have a fixed finite number of independent trials, 12. We have the success is that the archer here hits a bullseye. We have that the probability of success is 0.42. We want to find the probability that she does not get exactly 4 bullseyes. So I want to find the probability that X is not equal to 4. So let's look at the complementary event. 1 minus the probability that X is equal to 4. And so let's calculate this using the binomial probability formula. And so 1 minus N12 CR, which is 4, times P, which is 0.42 to the power 4. If I have a 42% chance of success, I have a 58% chance of failure. So Q is 0.58 to the power 12 minus 4, which is 8. And so I get 0.8027457773. Let me move my decimal place 2 places to the right. And so I have 80.27457773%. Let me round this to the nearest hundredth of a percent. And so I get 80.27%. Let me use the TI-83 / TI-84 to do this. So again, this is a binomial distribution with N equal 12, P equals 0.42. To find the probability X is not equal to 4, I'll do the complementary event. 1 minus binom PDF, 12, 0.42, 4. So let me do this on my TI-83 / TI-84. And so let me input 1 minus binom PDF. So second distributions. So the binomial PDF. I have here 12 trials. I have a 0.42 probability of success, and I do not want that X is equal to 4. And so I have 0.8027457773. Let me write that down on my iPad. And so we have here that 1 minus binom PDF 12, 0.42, 4 is 0.0827457773. Let me move my decimal place 2 places to the right. So 80.27457773%. Let's round to the nearest hundredth of a percent. And so 80.27%. Well, if you're going to be using Excel to do this, then again, we have a binomial distribution with N equals 12, P equal 0.42. I want to find the probability that X is not equal to 4. So I'll do 1 minus binomial distribution, 4, 12, 0.42, and we're going to be using a PDF, and so it'll be false. And so let me do that on my Excel. And so let me input 1 minus binomial distribution, so binom distribution. I have, I do not want X equal 4. I have 12 trials, and I have a probability of success of 0.42, and I want this to be a PDF, so this will be false. And so I have here 0.802 0.274578. Let me write that on my iPad. And so I have here 1 minus binomial of 0.42 false gives me 0.8027458. Let me move my decimal place 2 places to the right. And so I have 80.27458%. Let's round to the nearest hundredth of a percent. So 80.27%. We could also use Mathematica to do this. So if you were using Mathematica to complete this, then, well, again, we have a binomial distribution with n equal 12, p equal 0.42. We want to determine the probability x is not equal to 4. And so I will type in the command 1 minus PDF, binomial distribution, 12, comma, 0.42, comma, 4. And so let me do this in Mathematica. And so let me type in 1 minus PDF for the binomial distribution with parameters. There are 12 trials with a probability of success of 0.42. And I want to get rid of x equal 4. Oh, I'll get the exact amount, and I will also do this numerically. To 10 decimal places. Oops. Oh, there's 0.42. I don't have, it's already numerical. And so 0.802746. Let me type that into my iPad. And so we have 0.802746. Let me move my decimal place 2 places to the right. So 80.2746%. Let me round to the nearest hundredth of a percent. So 80.27%. I could also use R. So if I was using R, then we will solve the problem in the following fashion. Again, we have a binomial distribution. So n is equal to 12, p is equal to 0.42. I want to find the probability that x is not equal to 4. And so I'll do 1 minus d binom 4, comma 12, comma 0.42. So let me type that into R. And so I have here 1 minus d binom 4, comma 12, comma 0.42. And so I get 0.8027458. Let me type that into my iPad. And so I have 0.8027458. Let me move my decimal place 2 places to the right. And so I have 80.27458%. Let me round to the nearest hundredth of a percent.
Steve, we don't see the iPad.
80.27%.
Can you show the iPad?
Yes. Yes. Sorry.
Yeah, I'm keeping you honest here. Yeah, thank you.
I'm switching in between several things.
Yeah.
There's one thing that came up. I didn't hit it. Thank you.
You're welcome.
I'm using. I have to use more than one computer.
Yeah, I can
That's
see
why it
that.
takes a little while to transition. Okay, but thank you very much. Okay, so 1 minus d binom. Oh, yeah. So 1 minus d binom 4 comma 12 comma 0.42. So I get 0.8027458. Let me move my decimal place 2 places to the right. So 80.27458%, round hundredth of a percent. So 80.27%. If you were using StatDisk Online, then again, again, we will have a binomial distribution with n equal 12, p equals 0.42. I want to find the probability that x is not equal to 4. And so let me do that. And so here it is. So let's go up to analysis, click on probability distributions and binomial distribution. And so I have here that n is equal to 12. The probability of success, p, is 0.42. And I want x equal 4. So in this case, when you evaluate it, you get 1972542. And so I'm going to have to write that number in my iPad. But when I do that, I'm going to have to now actually do some arithmetic here. So when using StatDisk Online, it's going to require you to do a little bit of arithmetic. And so I have here 1 minus the number I just saw in StatDisk Online, 0.1972542, which gives me 0.8027458. Let me move my decimal place 2 places to the right. So 80.27458%. Let's round to the nearest hundredth of a percent, 80.27%. Problem number 13. A survey for brand recognition is done, and it is determined that 41% of consumers have heard of Dell Computer Company. A survey of 16 randomly selected consumers is to be conducted. For each such group, would it be significantly high to get 2 consumers who recognize the Dell Computer Company name? Why or why not? Explain your answer using descriptive statistics and or probability appropriately. If your reasoning requires a z-score, enter the z-score rounded to the nearest hundredth. If your reasoning requires a probability, enter the probability as a decimal rounded to the nearest 10,000. Well, this is going to be a binomial distribution since we are doing random selection. And so each of the trials will be independent. We have here that n is equal to 16. And we have success is that they have heard of the Dell Computer Company. And we have a fixed probability of success for each trial, 0.41. I want to find the probability that x is greater than or equal to 2. In this case, well, it'll be easier to use the complementary effect. So let's use the complementary effect. 1 minus the probability that x is less than 2. And so in this case, well, the things that are less than 2 are 0 and 1. So let's find the probability that x is 0 and the probability that x is 1. And so 1 minus the probability x is 0. So I have here is 16, and I want no successes, so 16C0. I have p is 0.41 to the power 0. If I have a 41% chance of success, I have a 59% chance of failure. So 0.59. 16 minus 0 is 16. Let's find the probability that x is equal to 1. So again, n is 16, c 1. I have p is 0.41 to the power 1. Again, q is 0.59 to the power 16 minus 1, which is 15. And so I get 0.99738732. Let's round this to the nearest 10,000s, 0.9974. Since this probability is greater than 0.05, that means that we are not in the rejection region. And so since we're not in the rejection region, no, this is not sufficiently high. No, this is not significantly high because the p-value is greater than 0.05. So this was not by pure chance. It was not due to statistical fluctuation. If you're using 84, then the way that you would approach this problem is, well, again, this is a binomial distribution with n equals 16, p equal 0.41. I want to find the probability that x is greater than or equal to 2. And so I'll look at the complementary event, 1 minus the probability that x is less than or equal to 1. So I'll type in the command, 1 minus binom CDF, 16, comma 0.41, comma 1 into the TI-83/84 calculator. So let me do that. And so let me type in 1 minus binom CDF. I have 16 trials. I have the probability of success is 0.41. And I want to get rid of everything less than or equal to 1. So in order to get everything greater than or equal to 2. And so I get 0.99738,732. Let me type that into my iPad. Yeah. And so I have here 0.99738732. Let's round this to the nearest 10,000ths, 0.9974. Since the probability x is greater than or equal to 2 is greater than 0.05, then no, this is not significantly high because the p-value is greater than 0.05. This was not by pure chance. It was not due to statistical fluctuation. If you were instead using Excel to answer this question, well, again, we have that this is a binomial distribution. We had that n here is equal to 16. P is equal to 0.41. I want to find the probability that x is greater than or equal to 2. And so let's do the complementary event. 1 minus the probability x is less than or equal to 1. So in this case, we're going to be using the binom distribution function. So binom.dist. And we're going to be doing an inequality. So we're going to be doing true. And so 1 minus binom dist. I want to get rid of everything less than or equal to 1. So 1, 16.41 true. Okay, so let's do this on my in Excel. Let's type this into Excel. And so 1 minus binom distribution. Oops. And we have, I want to get rid of everything less than the 1. I have 16 trials with fixed probability of success 0.41. And I want this to be cumulative. And so I get 0.99738 0.9732. Let me type that into my iPad. And so I have 0.99738,732. Round this to the nearest 10 thousandths. 0.9974. I have that since the probability that x is greater than or equal to 2 is greater than 5% alpha, then no, this is not significantly high because the p-value is greater than 0.05. This was not by pure chance. It was not due to statistical fluctuation. Okay, so if you were using, and again, this is a binomial distribution. We have that n is equal to 16, p is equal to 0.41. I want to find the probability that x is greater than or equal to 2. And so I'll use the complementary event, 1 minus the probability x is less than or equal to 1. And so 1 minus, well, we have an inequality, so we'll be using CDF. We have a binomial distribution, and we have parameters 16 and 0.41, and we want to get rid of everything less than or equal to 1. Okay, so let me do this in Mathematica. So let me type this in. And so I have here 1 minus CDF for the binomial distribution with parameters 16 and 0.41. And I want to get rid of everything less than or equal to 1. And so I have 0.997387. Let me type that into my iPad. And so I have 0.997387. Rounding to the nearest 10 thousandths, I have 0.9974. Since the probability x is greater than or equal to 2 is greater than alpha, then no, this is not significantly high because the p-value is greater than 0.05, the typical alpha value for alpha. This was not by pure chance. It was not due to statistical fluctuation. If instead you want to use R to answer this question, then, well, again, it's a binomial. This is a binomial distribution. N is 16, P is 0.41. I want to find the probability that X is greater than or equal to 2. So 1 minus the probability X is less than or equal to 1. So 1 minus P binom 1, comma 16, comma 0.41. And so let me type that into R. And so 1 minus P binom of 1, comma 16, comma 0.41. And so I get 0.9973873. Let me type that into my iPad. And so I have 0.9973873, rounding to the nearest 10 thousandths, I have 0.9974. And so the probability that X is greater than or equal to 2 is greater than 0.05. So no, it is not significantly high because the p-value is greater than 0.05. This was not by pure chance. It was not due to statistical fluctuation. If you decide to do this problem using StatDisk Online, then this is a binomial distribution. N is 16, P is 0.41. I want to find the probability that x is greater than or equal to 2. And so let me type that into StatDesk. And so if you type this into StatDesk, you have the following. So let's, again, you click on Analysis, Probability Distribution, the binomial distribution. And we have here that n is 16, p is, n is 16, p is 0.41, and x is equal to 2. And if you do that, well, to find the probability x is greater than or equal to 2, we have that the probability x is greater than 2 is equal to 0.9973873. And so let me type that into my iPad. So I have here 0.9973873. Round this to the nearest 10,000th, 0.9974. Since the probability x is greater than 2, is greater than 0.05, then we have that no, this is not significantly high because the p-value is greater than 0.05. This was not by pure chance. It was not due to statistical fluctuation. Problem number 14.
Steve,
a naturalist leads whale-watch trips every morning in March. Yes.
I'm just gonna
yes.
Okay.
Yes.
Okay, bye.
Okay. Bye right now. Okay. Problem 14. A naturalist leads whale-watch trips every morning in March. The number of whales seen has a Poisson distribution with a mean of 1.34. Find the probability that on a randomly selected trip, the number of whales seen is 4. Express your answer as a percentage rounded to the nearest hundredth. So we have a Poisson distribution. I have that mu is equal to 1.34. I want to find the probability that x is equal to 4. So let's use the Poisson probability formula. Mu to the x e to the minus mu over x factorial. And so mu here is equal to 1.34. X here is equal to 4. And so I get 0.0351765583. Let's move my decimal 2 places to the right. So 3.5176553.83%. Round this to the nearest hundredth of a percent. So 3.52%. If you were solving this using your TI-83, TI-84, then again, this is a Poisson distribution. Mu is equal to 1.34. I want to find the probability x is equal to 4. And so let's type in the following command. So I will type in Poisson, distribution. So I'll do the Poisson distribution. And this will be a Poisson PDF. Let's try that again. I'll type in the Poisson distribution, the Poisson PDF. I have that mu is 1.34 and x is equal to 4. And so you get 0.035176553. Let me type that into my iPad. And so we have I wanted to find the probability x is equal to 4. And so I did the Poisson PDF. 1.34 comma 4 is 0.035176553. Let me move my decimal place 2 places to the right. 3.5176553%. Let's round to the nearest hundredth of a percent. 3.52%. Using Excel, we again have that this is a Poisson distribution with mu equal 1.34 and x equals 4. So let's do Poisson.dist 4 comma 1.34 comma false. And so let me type that into my Excel. And so I have here Poisson distribution. And I have, I want to figure out when x is equal to 4, when mu is 1.34, and we want this to be a PDF, so false. And so 0.0351766. So let me type that into my, let me type that into my iPad. And so Poisson.dist 4 comma 1.34 false, 0.0351766, moving decimal place 2 places to the right, 3.51766%, round to the nearest hundredth of a percent, 3.52%. So if you're using Mathematica, then again, we have a Poisson distribution, mu equal 1.34. I want to find the probability x is equal to 4. Since it's equality, I'll be using PDF. So PDF, Poisson distribution, 1.34 comma 4. So let me type that into Mathematica. And so let me type in PDF for my Poisson distribution with parameter 1.34. And I want to find the probability that x is equal to 4. Oops. That x is equal to 4. So I get 0.0351766. Let me type that into my iPad. And so I have .0351766. Let's move my decimal place 2 places to the right. So 3.51766%. Let's round to the nearest hundredth of a percent. So 3.52%. If you're using R, then this is a Poisson distribution with mu equal 1.34. So I want to figure out the probability x is equal to 4. So you use d Poisson 4 comma 1.34. So let me type that into into R. And so I have here d Poisson 4 comma 1.34. And so I get 0.0351766. And so let me type that into my iPad. And so I have here 0.0351766. Let me move my decimal place 2 places to the right. So 3.51766%. Let's round to the nearest hundredth of a percent, so 3.52%. If you're using StatDisk Online, then let me type that in. And so we have Poisson distribution, mu equal 1.34. And so I want to find a probability that x is equal to 4. So let me do that. So let's go to analysis, probability distribution, the Poisson distribution. And so in this case, we have 1.34. And I want to figure out when x is equal to 4. And so I have here 0.03518. And so let me type that into my iPad. And so I have point 0.3518. Let's move my decimal place 2 places to the right. So 3.518%. Let's round to the nearest hundredth of a percent. So 3.52%. Number 15. Suppose the probability of contracting a certain disease is 1 in 50 for a new case in a given year. Approximate the probability that in a town of 119 people, there will be at least one new case of the disease next year. Express your answer as a percentage rounded to the nearest hundredth without the percent symbol. So let's recall the following: the approximation to the binomial distribution. If NP is greater than or equal to 5 and NQ is greater than or equal to 5, then we have that the binomial distribution with parameters N and P can be approximated by a normal distributions with parameters NP and radical NPQ, so long as we invoke continuity correction. If N were greater than or equal to 100 and NP were less than or equal to 10, then we can approximate the binomial distribution with parameters N and P by the Poisson distribution with parameter NP. So in this particular case, we have a binomial distribution with N equal 119 and P equaling 0.02. We want to calculate the probability that X is greater than or equal to 1. So let's look at the complementary event. 1 minus the probability that X is less than 1, which is the same as 1 minus the probability that X is equal to 0. Let's check if the Poisson approximation is applicable. Well, N is equal to 119, which is greater than or equal to 100. NP is equal to 119 times 0.02, which is equal to 2.38, which is less than or equal to 10. Therefore, the Poisson approximation is applicable. But notice, since NP is not greater than or equal to 5, that the normal approximation to the binomial distribution is not applicable. And so we will be using the Poisson approximation to the binomial distribution. Well, the parameter mu is equal to NP, 2.38. We have that P, we want to compute the probability that X is greater than or equal to 1, which is the same as, well, looking at its complementary event, 1 minus the probability X is equal to 0. And so let's use the Poisson approximation, the Poisson probability formula. So 1 minus mu, 2.38, to the X, 0, e to the minus mu, e to the negative 2.38 divided by x 0 factorial. And that's equal to, well, 9.9094494225. Let me move my decimal 2 places to the right. So 90.7449422.5%. Let me round that to the nearest hundredth of a percent. Since 4 here is less than 5, then we'll round this to 90.74%. Problem 16. Helene claimed that the expected value when rolling a fair die was 3.5. Steve said that this wasn't possible. He said that the expected value was the most likely value in a single roll of the die. And since it wasn't possible for a die to turn up with a value of 3.5, the expected value couldn't possibly be 3.5. Who's right? So, well, Helene is correct. The expected value is 3.5. The expected value is the average value. So for example, the average value of 3 and 4 is 3.5, even though it is neither a 3 nor a 4. Steve was describing a mode, whereas the expected value is a mean. The expected value is not the most likely value. It is the value that you would expect on average. 17. Draw the standard normal distribution. Shade the area between the z-score of negative 3.02 and negative 1.46. Find the shaded area, round to the nearest 10,000th. And so this is our standard normal curve. We want to find the area between negative 3.02 and negative 1.46. And so let's look at this. Well, I want to find this area, but well, I can't actually find that on this table because this table here only involves positive numbers. So by symmetry, I can look at the area between positive 1.64 and positive 3.02, find this area. This area will be the same as the area we want to determine. And so let's look at 3.02. So 3.02 is 0.4987. And let's also look at 1.46. And so I look here at 1.46 and I get 0.4279. And so let's subtract this area minus this area will give us this area here. So 0.4987 minus 0.4279 is 0.0708. We could also do this using technology. So I could use your TI-83, TI-84 to do this. And so let's do it. So first let's draw what we want to calculate. So we want to calculate the probability that Z is between negative 3.02 and negative 1.46. So I'll just do the command, well, the normal CDF between negative 3.02 comma negative 1.46. So let me do that on my TI-83, TI-84. And so we have here, let's click on normal CDF, so second bars. So, and then select my normal CDF. We want to go from negative 3.02 and negative 1.46. So I want the area between these two. And it's a standard normal curve, so I don't need to input the zeros and ones. So those are actually superfluous. They're there just because, well, they're unnecessary. So I get 0.070881136. And so let me write that down on my iPad. And so if I go to my iPad, I can do that. So I have here CDF gave me 0.070881136. Let me round this to 4 decimal places. So let's see. So I'll round this to the nearest 10 thousandths. And so I have here, well, 8 is greater than or equal to 5. So this 8 here becomes 9. And so I get 0.0709. I can also do this using Excel. And so if I use Excel, well, I want to find this area. Again, I want to find the area between negative 3.02 and negative 1.46. So I'll find the area less than negative 1.46, then subtract from it the area less than negative 3.02, and that'll give me the area in between these two. And so if I do that, let me do this on Excel. And so I'll type in normal distribution, but in this case, it'll be a normal, standardized normal distribution. So I'll do normal S distribution. I'll have here a negative 1.46, and I want this to be cumulative. I'll subtract from that, again, the normal distribution, standard normal distribution, negative 3.02, and I want this to be cumulative, so true. And so I get 0.070881116. And so let me write that down. So 0.07. So I do my normal S distributions, and I subtract the value at negative 1.46 minus the value at negative 3.02 to get 0.0708812. Rounding to the nearest 10 thousandths, I get 0.0709. Okay, I can also do this using Mathematica. And so let me do this using Mathematica. So again, I have here that, that this is my area I want to determine. So I want to find the probability that Z is between negative 3.02 and negative 1.46. And so let's subtract these two values of the normal distribution. Okay, so let me do that on using Mathematica. And so I'm going to type in subtract. And I want to subtract them. What do I want to subtract? Well, the CDF. And I'll do this for a normal distribution. And I don't need any parameters. And I want to subtract a negative 1.46 and negative 3.02. Okay, so if I do that, I get 0.0708812. And so let me write those values down. And so I have, oops. And so I have 0.07088812, rounding to the nearest 10 thousandths. I have 0.0709. I could also use R. And so if I'm using R here, well, let's draw the picture. So this is the area that we want to determine. I want to find the probability that Z is between negative 3.02 and negative 1.46. So I'll just do the P norm at negative 1.46, subtract from that the P norm at negative 3.02. And so let me do that. Let me type that into my into R. And so I have here P norm negative 1.46 minus P norm negative 3.02. Okay, so if I subtract that, I get 0.070881116. And let me type that into my iPad. And so I have here 0.0708816, round this to the nearest 10 thousandths, 0.0709. I can also do this using StatDisk Online. So let me do that. And so, well, we want to find this area. And so I want to find the probability that Z is between negative 3.02 and negative 1.46. For StatDisk, I'm actually going to have to write these values down. So I'm going to have to do this twice using StatDisk, and in between each of them, I'll have to write the values down. And so let's do it for negative 1.46. So I will go to analysis, go to probability distributions, go to normal distribution, and then I will type in the Z value, negative 1.46. And so I get the area to the left is 0.0715. I'll write that on a piece of paper. I will then write, well, the next 3.02. I'll write also 0.00126 on a piece of paper. And then what I'm going to do is I'm going to subtract those two values. So let me do that. So let me write those two values down and subtract them. And so I have here a 0.07215 minus 0.00126 gives me a 0.07089, which I'll round to 0.0709. Problem number 18. Draw the standard normal distribution. The right is the is 0.1160. Find the Z-score, round to the nearest hundredth. So let me use table 3. So let me draw my normal distribution. And so I have here a normal distribution. And I have that the area here to the right is 0.1160. Well, when I look in the table, just find the area of a right tail, I can only find areas in between. So let's find the area in between 0 and whatever the critical value is. Well, I know the area to the right of 0 is 0.5 by symmetry. Therefore, we have that the area between 0 and the value we want to determine is 0.5 minus the 0.1660. So I want to look for 0.3340 in my table. So let's look for 0.3340, and there it is in my table. And so I have a corresponding z-value of 0.97. And so my z-value is 0.97. I could also do this using technology. And so I could use my TI-83/84. So let's do that. So using the TI-83/84, let me draw my normal distribution. So I could either find the value doing the inverse norm of 1 minus the 0.1660, or I could do the inverse norm of 0.1660 using the right command. That's only if I have the latest version of the TI-84. So let me do that. And you'll notice that you'll get both the same answers doing it either way. And so let me type in the inverse norm. Let's do the inverse norm of 0.1 minus 0.1660. It's standard, so I won't need to change any of these. And this will be my left tail. Doesn't really matter. And so I can issue this command, or get rid of some things here. I could also just have said inverse norm of 1 minus 0.1660. Notice it gives me the exact same answer. Or, so this, the inverse norm of 1 minus the 0.1660, that is a command that could be used on the TI-83. So I could also do, again, the inverse norm of 0.166. And these will all be the same, except the tail will be the right tail. And so if you do 0.1660, but you have a right tail, then you get, again, the same answer. So notice that for all of them, they're all 0.970932795. And so they're all the same. So it really doesn't matter which one that I did. So let me put those down. So I have here, let's write these out. I have 0.9709932795, which I'll round to the nearest hundredth as 0.97. I could do this using Excel. And so let's do this using Excel. And so let me draw my normal distribution. And so I have here, well, this is my normal distribution. And the area that I want is this area here. I want to find a z-value for this area. So, well, I'll have to do what I did basically with the TI-83. I'll have to do the normal normal, or the inverse norm. So I'll have to do my inverse norm for not the right tail, but for the left tail. So I'll have to subtract this from 1. And so if you do that, well, let's do that. And so I'm going to be using the standardized inverse norm. And so Let's do norm S inverse, there it is, of 1 minus 0.1660. And you get 0.97009328. Okay, so let me write that down. There it is. So let me write that down. And so 0.9700933, and rounding to the nearest hundredth, 0.97. I could also use Mathematica to do this. And so first let me write out, let me graph what we do to determine. So my area is 0.1160. And just like with Excel, I'm going to look at, well, the area of the left tail rather than right tail. And so the inverse CDF of the normal distribution at, well, 0.8340. So let me do that. So I'm going to type in the inverse norm, the inverse CDF of the normal distribution. I don't need any parameters, it's standardized. And this is 1 minus 0.1660. And so I get 0.970093. And let me write that down. And so I have 0.970093, rounding to the nearest hundredth, 0.97. We could also use R to do this. And so let me graph the normal distribution. So my area of my right again is 0.1. I'll have to do it like what I did with Mathematica. So I'll use the Q norm of, well, a point of the left tail, the 0.8340. So let me do that. So let me type in Q norm. And so I have here Q norm of 1 minus 0.1660. And so I get 0.9700933. And let me type that in to my iPad. And so I have here 0.9700933, rounding to the nearest hundredth, I have 0.97. I could also do this using StatDisk. And so let me use StatDisk. So first, well, we're trying to find the area of the right tail, but we'll have to look at the area. Well, actually we don't. We'll look at the area of the right tail. And well, to do that, 1 minus 0.1660. And so I'll have to do that by hand. And so I have here 0.8340. And now let me go to StatDisk Online. So like before, I'll go to analysis, probability distributions, normal distribution. The cumulative area to the left is the 0.8340. Let me evaluate that. And I get, if you look, the Z value is 0.97009. And let me write that into my iPad. And so let me write that down. And so I have point 97009, rounding to the nearest hundredth, 0.97. Problem number 19. Suppose that replacement times for washing machines are normally distributed with a mean of 8.8 years and a standard deviation of 2.4 years. Find the replacement time that separates the top 1.1% from the rest. Round to the nearest hundredth. Okay, so let's do that. And so we want, well, that this area is 1.1%, 0.011. Let's subtract that from 0.5 to get 0.4890. And so this is an area that we can look at in table 3. So let's look for 0.4890. Here it is. That corresponds to 2.29. So I have here that Z is 2.29. I want to figure out the X value, where the mean is 8.8 and the standard deviation is 2.4. Oops. And so the mean was 8.8 and the standard deviation was 2.4. Therefore, we get 14.296, which we round to the nearest hundredth, 14.30. Let me use the TI-83, TI-84. So I want to find this area. So if you're using the 83, you'll need to calculate, or an older version of the 84, you'll need to calculate 1 minus this to get the area of a left tail. And so 0.9890, or with the, well, more modern version of the 84, you can just leave it at that. I have a mean of 8.8 and a standard deviation of 2.4. And so let me type in the inverse norm. You could do, well, for the latest version where you have a command where you can issue something called write. I'll just do the inverse norm of 0.011, comma, 8.8, comma, 2.4, comma, write. If you have an older, say anything from the TI-83 or above, you would just do 1 minus the 0.011, comma, 8.8, comma, 2.4. Okay, so let me do that. So let me do the inverse norm. Well, and I guess I'll do both ways doing it. And so let's do the inverse norm. Well, actually, I've already done it before. So maybe I'll just do the inverse norm of 0.0110. The mean is 8.8. And the standard deviation was 2.4. And we want a right tail. And so you get 14.2968829, or you could do the inverse norm of 1 minus 0.0110 and have it as a left tail. Or you could issue actually the same thing. Let's see, and not, you don't really need a left. Okay. And so, again, you get the same thing. So you will get 14.29688.291. And so let me write that on my, on a piece of paper. And so I have here 14.29688.291, which I can round to the nearest hundredth, as 14.30. I could also use Excel to do this. And so I will need to look at 1 minus this. And so I'll have to look at the left tail. And so, again, the mean is 8.8, standard deviation is 2.4. So we'll be doing the normal, but in this case, not S, because we have, well, the mean and standard deviation is not 0 and 1. And so we'll do it with the inverse norm and the regular one, not the standardized one. Okay, so let's write that into my into Excel. And so I have the inverse norm. So norm inverse. So we're going to be using this command. And we have here 1 minus 0.0110. The mean was 8.8. And the standard deviation was 2.4. And so I get 14.2968829. Let me write that down. And so we have 14.296883, which I can round to the nearest hundredth as 14.30. We can also use Mathematica to do this. And so the mean was 8.8. The standard deviation is 2.4. We want to find this critical value here, where the area of the right tail was 0.0110. And so I'm going to use the inverse CDF of the normal distribution with the parameters 8.8 and 2.4, and the area of the left tail. And so let me type in those commands. And so we're going to be using the inverse norm. And so the inverse CDF for the normal distribution with parameters 8.8. The mean is 8.8, standard deviation is 2.4. And the area is 1 minus 0.0110. And so I get 14.2969. And so let me write that down on a piece of paper. And so we have 14.2969, which I can round to the nearest hundredth, 14.30. We could use R to do this. So again, we have that the mean is 8.8 and the standard deviation is 2.4. We want to find the critical value where the area of the right tail is 0.0110. Let's figure out the area of the left tail. And so, and then issue the Q norm. So let's type in Q norm into R. And so I have here Q norm of 1 minus 0.0110. The mean was 8.8 and the standard deviation was 2.4. And so I get 14.29688. And so let me write that down. So I have here 14.29688. I can round this to the nearest hundredth. And so I get 14.30. I can also use StatDisk online to do this. So again, mu is 8.8, Sigma is 2.4. I want to find the critical value where the area of the right tail is 0.0110. And so I will have to write down on a piece of paper mu, which is 8.8, sigma, which is 2.4. Then I'll have to look at StatDisk online and look for what my critical value is. And so let me subtract 1 minus 0.0110. I have to do that on a piece of paper, and I get 0.9890. I can use that value now to figure out my z value, which I will write down. And so I will type in, again, you go to analysis, probability distribution, normal distribution, and you type in 0.9890, and you find a z value of 2.9037. And then let me type that down. I'm going to now have to use that in a calculation. And so I'm going to have to actually calculate this. And so let me write this down, the 2.29037. Let's multiply it by 2.4, add 8.8 to it. So I get 14.296888, which I can round to 14.30. 20. The weights of the fish in a certain lake are normally distributed with a mean of 5.6 pounds and a standard deviation of 1.2 pounds. If 11 fish are randomly selected, what is the probability that the mean weight will be more than 4.5 pounds? Express the answer as a percentage rounded to the nearest hundredth without the percent sign. And so let's recall the formula for the parameters of a sampling distribution of sample means. And so the mean for the sampling distribution of all possible sample means is the mean of the population, mu. The standard deviation for the sampling distribution of all possible sample means is sigma divided by the square root of n. If the population size is infinite, or a simple random sample with replacement, it is equal to sigma over the square root of little n times the square root of big N minus little n over big N minus 1, if the population is finite and if we're doing a simple random sample without replacement. So in this case, they don't tell us the size of the population. Therefore, the population is infinite. And so this is the formula that we'll be using to determine the standard deviation for the sampling distribution of all possible sample means. Well, we have that the population mean is 5.6 and the population standard deviation is 1.2. So mu is 5.6 and sigma is 1.2. We have that the population is normally distributed. Therefore, we're sampling from a normally distributed population. Our sample size is 11. So little n is 11. We want to find, so since the parent population is normally distributed, then the sampling distribution of all possible sample means is also normally distributed with mean and standard deviation as follows. And so we want to find the probability that the sample mean is greater than 4.5 the mean for the sampling distribution of all possible, the standard deviation for the sampling distribution of all possible sample means. Well, if you recall, we found out that the formula that we're going to be using for the standard deviation for the sampling distribution of all possible sample means is just sigma over the square root of n. So sigma, well, we have the population standard deviation. This is equal to 1.2 divided by the square root of the sample size, which is 11. 0.3618136,135. So let's figure out Z. So if I'm going to be using a table, then I need to standardize. And so let's standardize this random variable. So Z equal X minus mu over sigma. In this case, we're using sample means. So mu is equal to the sample mean minus the mean for the sampling distribution of all possible sample means over the standard deviation for the sampling distribution of all possible sample means. And so 4.5 minus 5.6 divided by 0.3618136,135. Negative 3.040239,391. So to find the probability that that X bar, the sample mean, is greater than 4.5, I just want to figure out the probability that Z is greater than a negative 3.040239,391. Well, that's the same as, it really doesn't matter. Doing 1 minus the probability that Z. So I can use my, if I try to use my table, I notice that my table ends at, well, it doesn't have 3 or above. So it ends right before we get to 3. So I can't actually look at the area in the tables because they're not there. So let me use the Pade approximation. And so 1 minus, and let's plug it in. So it's e to the minus z squared divided by 2, all divided by the absolute value of z times the square root of 2 pi times z squared plus 2 over z squared plus 3. And so I get 0.9999883376. Move my decimal place 2 places to the right. So 99.99883376%, round to the nearest hundredth of a percent. Now this makes it 1 larger, so it's 100%. Or if I round to, let's round to 3 decimal places, it is 99.999%. Let me use my TI-83, TI-84 to do this. And so the mean for the sampling distribution of all possible sample means is 5.6. The standard deviation for the sampling distribution of all possible sample means is 1.2 divided by the square root of 11. So the probability that the sample mean is greater than 4.5 is just 0.5 plus the normal CDF, going from 4.5 to 5.6. Oh, I didn't draw it. Okay. Oops. Let me draw this. Okay, so I have here let's say X. So I want to find the, or X bar. I want to find the probability that the sample mean is greater than 4.5. And I have a sample mean, I have the mean is 5.6. So the area greater than 5.6 by symmetry is 0.5. Let's use normal CDF to find, so this will be found by my normal CDF. I'm finding the area from 4.5 to 5.6. When I add to that 0.5, that will give me this total area. Okay, so let me do that. I don't know why that did that. And so let me type in 0.5. I also could have gone from 4.5 to infinity, but, wait 1 second. Let me just check something. Share content. Okay. And so let me do 0.5 plus normal CDF. I'll start at 4.5. Huh. 4.5. There it is. I'll end at 5.6. The mean is 5.6. The standard deviation is 1.2 divided by the square root of 11. So I get 0.99811. I'm sorry, 0.9988179806. Okay, so let me type that in. And so I have here 0.9988179806. Let me move my decimal place 2 places to the right. So I have a 99.88179086%. And so 99.88%. Using Excel, the mean for the sampling distribution of all possible sample means is 5.6. The standard deviation for the sampling distribution of all possible sample means is 1.2 divided by the square root of 11. I want to find the probability that X is greater than, that X bar is greater than 4.5. This is the same as 1 minus the probability that X bar is less than 4.5. And so let's do 1 minus the normal distribution. I'll start at 4.5. I'll find everything less than 4.5. I want to get rid of that. With a mean of 5.6 and a standard deviation of 1.2 over the square root of 11. And I want this to be a cumulative area that I'm finding. So let me type that into my, into Excel. And so let's type in 1 minus the normal distribution. And we want to get rid of everything less than 4.5. The mean is 5.6. And the standard deviation was 1.2 divided by the square root of 11. And I want this to be true, cumulative. I want this to be cumulative. And so I'll get 0.99881805. And so let me type that into my iPad. And so I have here 0.998818, which I can move 2 decimal places to the right, 99.8818%, which I can round to 99.88%. And so I have here that the mean for the sampling distribution of all possible sample means is the mean of the population, 5.6. The standard deviation for the sampling distribution of all possible sample means is the standard deviation, since we have a infinite population, is the standard deviation of the population divided by the square root of the sample size, 1.2 divided by the square root of 11. And so I want to find the probability that the sample mean is greater than 4.5. Let me look at the complementary event. 1 minus the probability that the sample mean is less than 4.5. And so I'm going to type in 1 minus CDF of the normal distribution with parameters. The mean is 5.6. The standard deviation is 1.2 over the square root of 11. And I'll get rid of everything less than 4.5. And so let me type that into my computer. Oops. I hit the wrong thing. Mathematica. Where? Oh, here it is, Mathematica. Okay, good. So let me do 1 minus the CDF for the normal distribution, where the mean is 5.6 and the standard deviation is 1.2 over the square root of 11. And we want to get rid of everything less than 4.5. Okay, so let's do that. And so, oops, if I do that, I have 0.998818. Let me type that into my piece of paper. And so I have here 0.998818. Let me move my decimal place 2 places to the right. 99.8818%, rounding to the nearest hundredth. We can also do this using R. And so the mean for the sampling distribution of all possible, the standard deviation for the sampling distribution of all possible sample means is the standard is sigma over the square root of n, 1.2 over the square root of 11. And so I want to find the probability that X bar is greater than 4.5. I'll look at the complementary event 1 minus the probability that X bar is less than 4.5. And so I'll type in the command 1 minus P norm. I want to get rid of everything less than 4.5. The mean is 5.6 and the standard deviation is 1.2 divided by the square root of 11. And so if I type that in, I'll get the following. And so 1 minus P norm of 4.5. I want to get rid of everything less than 4.5. The mean is 5.6 and the standard deviation is 1.2 divided by the square root of 11. Okay, so I get 0.998818. Let me type that into my piece of paper. And so I get 0.998818. Let me move my decimal place 2 places to the right. So I have 99.8818%. Let me round to the nearest hundredth. And so I have a 99.88%. I can also do this using StatDisk Online. And so the mean for the sampling distribution of all possible sample means is mu 5.6, the standard deviation. The sampling distribution of all possible means is 0.3618136.135. So before I can use StatDisk Online, I have to compute Z, I have to normalize. And so X minus mu over sigma. So I have here that the sample mean is 4.5. The mean for the sampling distribution of all possible sample means 5.6. The standard deviation for the sampling distribution of all possible sample means 0.361836135. And so I get a negative 3.040239391. I want to find the probability that X bar is greater than 4.5. That's the same as find the probability that Z is greater than a negative 3.040239391. So let me plug that into my, type that into my StatDisk Online. And so first, I go up to analysis, probability distributions, normal distributions. I'll type in the Z value of negative 3.040239391. And if I evaluate that, I get that the area to the right is 0.99882. And so let me write that on a piece of paper. And so we have 0.99882. And so let me move my decimal place 2 places to the right. 99.882%, round to the nearest hundredth of a percent, 99.88%. 21. Approximate the probability that in 53 tosses of a fair die, more than 12 ones will be obtained. Express the probability as a decimal rounded to nearest thousands. Well, this is going to be a binomial distribution. N in this case is 53. Success in this case is that you, that when you toss a coin, you get a 1. The probability of getting a 1 in each trial is 1 out of 6. And so the probability of success is 1 out of 6. And you want to find what's the probability that you get more than 12 of these successes. So let's check if the normal approximation to the binomial distribution is applicable. So N times P, so 53 times 1/6, 8.8333 is greater than or equal to 5. N times Q, 53 times, if you have a 1 out of 6 chance of having success, then you have a 5 out of 6 chance of having failure. And so I get 44.166, which again is greater than or equal to 5. So yes, the normal approximation to the binomial distribution is applicable. Therefore, we can invoke a continuity correction. Therefore, let's invoke continuity correction. And so we want to be greater than 12. So we're starting greater than 12. And so we're starting here greater than 12, which means that, well, if I look at this and I look at a continuous approximation, the continuous approximation is actually starting at 12.5, halfway between 12 and 13. And so X here is 12.5 with continuity correction. So I want to find the probability that x is greater than 12. Having that x here is a binomial random variable. When x here is a normal random variable, that's the same as finding the probability that x is greater than or equal to 12.5. And so let's find the parameters for this normal random variable, this normal approximation. So mu is equal to NP, 53 times 1 over 6, 8.833. Let's find the variance. The variance is NPQ, 53 times 1, 6 times 5, 6, 7.36111. So let's find the standard deviation. So let's take the square root of the variance, 2.713136766. So let's determine z. Z is equal to x, 12.5, minus mu, 8.833, divided by sigma, 2.713136766. I get 1.351449257. So I want to find the probability here that x is greater than 12. And so that's the same as finding the probability that z is greater than or equal to 1.351449257. So let's look at that on my table. I'm going to have to subtract this from 0.5. So if I look at the one, this is between 1.35 and 1.36. So 1.35 and 1.36. And I'll need to interpolate the 0.4115 and the 0.4131. So P is equal to 0.4115 plus 0.4131 minus 0.4115 divided by 1.36 minus 1.35 times 1.35144927 minus my 1.35. And so I get 0.41173118811. Subtract that from 0.5 to get what we want. And so I get 0.08826811189, rounded to the nearest thousandths. I get 0.088. Problem 22. Let x and y be independent random variables. Prove that the variance of x plus y is the variance of x plus the variance of y. Well, first off, note the following, that if x and y are independent random variables, then the expected value of x and y is the expected value of x times the expected value of y. So the variance of x plus y is equal to the expected value of x plus y quantity squared minus expected value of x plus y squared. And so that was one of the formulas from section 5.1 for the variance. Next, let's use the special product formula. And so let's use the perfect square trinomial formula. X plus y quantity squared is, well, x squared plus 2xy plus y squared. We also know that the expected value of x plus y is the expected value of x plus the expected value of y. So now, let me use the special product formula to simplify this. And so, again, by the perfect square trinomial formula, this is equal to the expected value of x squared plus 2 times the expected value of x times the expected value of y plus the expected value of y quantity squared. Again, by the properties of expected value from section 5.1. Since the expected value is linear, we have that the expected value of this quantity is just the expected value of x squared plus bringing out the constant on front, 2 times the expected value of xy plus the expected value of y squared. Let me bring the negative sign inside the parentheses. So this is minus the expected value of x squared. This is minus 2 times the expected value of x, expected value of y. This is minus expected value of y squared. And let's group things together. So this is expected value of x squared. This is 2 expected value of xy. And this is expected value of y squared. Well, note that the expected value of xy is the same as expected value of x and expected value of y, because x and y are independent. This is the variance of x, and this is the variance of y. And that's what you wanted to prove. Problem 23. Prove the following. If x is a Poisson random variable, then the variance of a Poisson random variable is equal to mu. And so recall that if x were a Poisson random variable, then the expected value of a Poisson random variable is just mu. Well, the variance of x, again, by the properties that we proved back in section 5.1, is the expected value of x times x minus 1 plus the expected value of x minus expected value of x squared. The expected value of x is mu. The expected value of x is mu. By definition, the expected value of, well, let's say x times x minus 1 is x times x minus 1 times the probability of x. Well, the probability of x by the Poisson probability formula is mu to the x e to the minus mu over x factorial. And this is from x equaling 0 to infinity. Now, I can bring e to the minus mu out in front of the summation, and I can bring mu squared out in front of the summation. By the properties of summation, I can bring constants outside of summation. If I do that, then this is gone, and I'm subtracting two, I'm taking 2 of the mu's away, so this is mu to the power x minus 2. I can write x factorial as x times x minus 1 times x minus 2 factorial. Notice that when x is 0, 0 times anything is 0. When x is 1, 1 minus 1 is 0 times anything is 0. So really, I can start from 2 and go to infinity. Good. Next, let n equal x minus 2. And so wherever I see an x minus 2, I replace x minus 2 by n. When x is 2, 2 minus 2 is 0, so n is 0, 0. When x is infinity, well, infinity minus 2 is still infinity, so n is equal to infinity. The sum in equaling 0 to infinity of mu to the n over n factorial is just e to the mu, which cancels with e to the negative mu. But then mu squares cancel, and so you get mu. And that's what you wanted to show. 24. Prove the following. PQ is maximized when P is equal to half. Well, let's look at P times Q. Q is 1 minus P. So let me multiply P inside the parentheses. So this is just P minus P squared, which is a negative P squared plus P. Therefore, this is quadratic. So PQ is quadratic in P. It is a parabola. And since the coefficient in front of the P squared is negative, it is a parabola that's going down. Therefore, the graph of PQ is a parabola. Since the leading coefficient is less than 1, the graph of PQ is a parabola that opens down. Therefore, the maximum of PQ occurs at the vertex. So therefore, PQ is maximized when, well, X is equal to negative B over 2A. So when P is equal to a negative B, 1 over 2 times A, negative 1. The negatives cancel, so you get a P is equal to 1/2. So I've shown that PQ is maximized when P is 1/2. Problem 25. The scores on the graduate record examination are normally distributed with a mean of 565.341 and a standard deviation of 31.056. Use the standard normal table and linear interpolation to find the percentile rank of a student whose score is 552.9. Write the percentile to the nearest thousands. So we have a normal distribution with mu equal 565.341, sigma equaling 31.056. I want to find the probability that X is less than 552.9. So Z equal X minus mu over sigma. 552.9 minus 5.341 over 31.056, a negative 4.005989181. And so the probability that X is less than 552.9 is the same as the probability Z is less than a negative 0.400598981. By symmetry, that's the same as the probability that Z is greater than 0.400989181. And so I can just find the area of this right tail by doing 0.5 minus the area between 0 and the number 0.400598981. So let's use linear interpolation. And so, I just showed these in graphs. And so I want to find the area to the right, to the left of 559.2. Standardizing it, that's the same as the area to the right of a negative 0.400598891. By symmetry, that's the same as the right tail for this. So I change it from a left tail to right tail. And I then just want to find, doesn't show it. I then just want to find this area here. Okay, and so let's find what this area is here and subtract it from 0.5. Minus whatever area is over here. Okay, so let's look at 0.4. This is somewhere between 0.40 and 0.41. So somewhere between 0.40 and 0.41. So 15.1554 and 0.1591. So P is equal to 0.1554 plus 0.1591 minus 1.1554 divided by 0.41 minus 0.40 times this. The 0.400598981 minus the 0.40. 0.155621597. Subtract that from 0.5 to get 0.3433784,003. Let's move my decimal place 2 places to the right. 34.43784,003%. Let's round to the nearest thousandth of a percent. And so 8 here is greater than 5. So this 7 becomes an 8, 34.438%. And that is it.